Good day, everybody. In the previous chapter, we talked about how to balance a chemical reaction. We also talked about different types of chemical reaction and different ways to represent the same chemical reaction. For example, we can represent the chemical reactions in the molecular equation, or complete ionic equation, or net ionic equation. In the different types of chemical reactions, we talked about precipitation reaction. We also talked about the gas evolution reaction, etc. In today's lecture, we'll be focused on the quantitative aspect of a chemical reaction, and we are going to show you how to calculate how much product can be produced in a chemical reaction, or how much reactants is needed for a chemical reaction to produce a certain amount of products. Before we go into the details, I would like to do some reviews about the quantitative calculations we have done before. The first type of calculation we talked about is the unit conversion. For example, feet converted to inch, or inch converted back to feet. This is similar to inch converted to centimeter, or centimeter converted to inch. Basically, this is the one-step unit conversion. The second type is if the two units you are trying to interconvert are not directly related, you cannot find a numerical relationship between those two directly, then you're trying to find another unit that can connect those. So for example, if you want to convert feet to centimeter first, usually you don't remember this relationship. 1 foot is how many centimeter. Usually most people will not have this available. So what you can do is you can convert foot to inch first, then inch being converted to centimeter. You can also go backward. That's why I use arrows on both ways. All right. The third type of calculation we talked about is the squared. For example, convert square feet to square inch, or you can do the cubed units. All right. In this kind of situation, the conversion factors must be squared as well for this conversion. Please refer to your previous videos for more details. Next, we also talked about something that's more related to chemistry. 1, 2, 3, it's more like math, but starting from the next relationship we talked about, it's more related to chemistry. For example, we learned how to convert a mole to a number using Avogadro's number. Okay, we can also convert a number back to mole, and over here what we use is 1 mole is Avogadro's number, a very large number, 6.022 times 10 raised to 23. Okay, if you refer to a specific atom or molecule, you would be able to say 1 mole of anything. For example, 1 mole of carbon is 6.022 times 10 raised to 23 number of carbon, etc. Okay. The next thing we talked about is actually interconvert mole with grams. So you can convert mole to grams, or grams back to mole. All right, using so-called molar mass. So molar mass is really important, but this molar mass is implied in the formula. You will have to calculate this. Basically, what this tells you is 1 mole of anything is formula grams of that thing. Then similarly, for example, sometimes you will have to use multi-step conversion. If you want to convert grams to certain number, you cannot do this directly. For example, if I ask you let's say, do this question, how many molecules of CO2 in 24.6 grams of CO2. So basically you're given grams, we want you to find a number, right? We want to find a number. So you cannot do this conversion directly. Hashtag represents a number. So what you need to do is actually you'll convert grams to mole first and mole back to a number. So when you do this calculation, it will be more straightforward. Okay. Of course, for details, please refer to chemical composition. So with all this, we are ready to talk about the new quantitative calculation we will be doing in this chapter. That is what we are going to do for today. We are going to introduce to you the quantities in chemical reaction. Okay. So in the chemical reaction, the most important relationship is the molar relationship. So in the chemical reaction, for example, water decomposes to hydrogen and oxygen. You balance this reaction. So what we can get from this balanced equation is, for example, for every 2 moles of water, you will generate 1 mole of oxygen. Or if you look at the water and the hydrogen relationship, you would have for every 2 moles of water, you will have 2 moles hydrogen produced. So basically, for any chemical reaction, if it's balanced, we can read the molar of one substance. Let's use A to represent it. Is going to be related to molars of substance, another substance. I'm going to use B to represent it. Okay. So with this molar relationship, we will be able to do most of the calculations that will be involved in this particular chapter. All right. So hopefully I am able to show you the progression between all these calculations. In the end, we will be talking about this new relationship that is involved in the chemical reaction. But before we do that, I want to introduce to you some other basics for a chemical reaction. First, I'm going to talk about global warming. Global warming is generated by a chemical reaction which produces carbon dioxide. For example, the combustion of fossil fuels, okay, such as octane, it will produce water together with carbon dioxide as the products. And carbon dioxide is one of the so-called greenhouse gases because it is believed to be responsible for global warming. Basically, global warming is the situation as if you have the glass in the greenhouse. So when the sunlight comes in, the energy of the sunlight is absorbed. But when the heat is trying to escape, it's blocked by the glass. So it's sort of like a glass house. So this is so-called a greenhouse effect. The energy is absorbed. However, it's not escaping as effectively. So basically, the outgoing heat is trapped by the greenhouse gases such as CO2. We have some other different types of greenhouse gases. CO2 is only one of them. For example, methane is also considered as a greenhouse gas. If given specific amount of fuel, we can actually calculate how much carbon dioxide will be generated. And this type of calculation, we call them chemical stoichiometry or simply stoichiometry, which is telling you the quantitative relationship between different chemicals. or more specifically, between the reactants and the products. With a balanced chemical reaction, we can predict the amount of products that can be formed based on the amount of reactants. We can also find out how much of the reactants are needed to form a given amount of products. So let's look at one example. For example, when you look at the reaction between hydrogen and nitrogen, when you read this chemical reaction, we can read this as 3 moles of hydrogen reacting with 1 mole, that one is not written, 1 mole of nitrogen to produce 2 moles of ammonia molecules. So the relationship, if we are looking for example, if we are looking for the relationship between hydrogen and nitrogen, okay, we do know that would be apparently a 3 to 1 relationship. Okay, so you can write this down as 3 molecules versus 1 molecule, or you can write down 3 moles versus 1 mole. Do you remember? Similarly, if you want to, although we don't use it, you can also write down 3 dozen hydrogen molecules will be related to 1 dozen nitrogen molecules. Okay, so do remember, mole is simply a large number. Another example, for example, if you want to look for, let me erase this for now. If you are looking for the relationship between nitrogen and ammonia, what's the mole relationship? That would be 1 mole of nitrogen is related to 2 moles of ammonia. So you can write it this way. 1 mole of nitrogen is related to 2 moles of ammonia. Ammonia is NH3. Okay, so basically a balanced chemical reaction gives you a key piece of information, which is the mole relationship between the chemicals, more specifically the mole relationship between the reactants and or substance products. Let's do a chemical reaction based on this analysis. So the same chemical reaction we are discussing over here. So just do not look at the answer key yet. Let's analyze this equation, okay, by looking at the question first. So we are given 3 moles of nitrogen. Then we ask you how much ammonia can be produced. Okay, so basically here you have the moles of nitrogen, but you are asked to find out the moles of ammonia. So the relationship when you work on it should be, you always write the mole relationship first. I want you to be 100% clear. When you do the chemical stoichiometry or the calculation based on a chemical reaction, I want you to always write the pertinent mole relationship first. Mole relationship. That's the key. All right. So for example, you are given moles of nitrogen. So I want you to write moles of nitrogen to begin with. Now you want to convert this to something that is related to ammonia. So that's, you want to relate nitrogen to ammonia. So the first relationship we should always write out is the mole relationship between the 2 substances. So we are given nitrogen, and then we want to find out moles of ammonia. Okay, so that's the how you get this solution map as you see on the right side over here. So that's my first step. The second step would be, what type of number are you really given? We are given, I want you to look at, we are given moles, 3 moles to begin with. So That means we are given moles of nitrogen to begin with. That's exactly where you start. Okay? So you want to convert it to moles of ammonia. So do remember, if you want to convert this unit to a different one, you have to cancel out the same unit. So you use the mole relationship to do that. Okay, now we can put in the real numbers. We actually have 3 moles of nitrogen, and then what's the relationship between the ammonia and the nitrogen? For this, you will have to look at the mole relationship from the balanced chemical reaction. So we have 1 mole of nitrogen, okay? 1 mole of nitrogen. So when you look at this, it's 1 mole of nitrogen. That's where you get that 1. Okay. What about ammonia? Ammonia is 2 moles. So you get the ammonia from the balanced equation. That's 2 moles. That's exactly why you have the answer key listed as this. So eventually you find out you have 6 moles of ammonia produced from 3 moles of nitrogen with enough hydrogen. Okay, right. So this relationship is basically you convert a mole to a different mole. We could have a more complicated situation. For example, you could be asked to convert mass or grams of one substance A to a different substance. But no matter what you do, I always strongly suggest write out the key relationship to begin with. Then decide what you're going to do next, depending on what information is given. Always write out the key relationship, which is a mole relationship. Okay, so let's look at another example by analyzing this step by step. Okay, all right. For example, what's the mass of carbon dioxide? Mass means you are gonna find out how many grams of carbon dioxide, okay, is emitted by the automobile for certain grams of octane. Okay, octane, by the way, is a C8H18. So first thing, you will have to write the correct equation, which is provided above, right? So it's balanced the chemical equation as well. Then before we do analyze this, you remember we are talking about octane that is given. So for when you write a solution map, I want you to write moles of octane to begin with. Why? Because that is known. It gives you something that is known about that thing. So always write the mole relationship to begin with. And this is converted to something that is related to carbon dioxide, because that one, it's asking you a question mark of this. So how many of whatever related to CO2? So that's the core relationship. Okay. Now basically, if you give me moles of octane to begin with, then you want to find out moles of CO2. That would be the only relationship that you need to know, right? However, it's the number of grams of octane. So you need to extend the left side for one more step, because grams of octane can be converted to moles. Grams converted to mole or mole to grams, we use molar mass relationship. Okay, hopefully you do recall this. All right, on the right side, do we stop it over there or do we extend it to grams? It depends, because here in this question, I want you to read this. This question actually asks you, what mass of the carbon dioxide is emitted. So it's asking you got to convert this moles of CO2 into grams. That means to that core relationship, mole and a mole relationship, okay, to that core relationship, mole and mole relationship, you will have to convert this mole of CO2 back to grams of CO2. So that's exactly what I'm going to do. This core relationship to the right side, because you need to convert to grams of CO2, you need to extend it. But we start with the molar relationship. That's the key to simplify every question. All right, so according to what we have over here, that's 3-step procedure. The first step, okay, is convert grams to mole. Then you might be wondering, hey, so let me write this directly. So how many grams do you have? 5.0 times 10 raised to 2 grams of octane. All right, so you write this down. That's my first step. I need to convert to molars. Okay, but how do you convert to moles? That's molar mass. So basically, I'm going to convert grams to mole. You will have to cancel out the previous step. Okay, please specify octane. By the way, it's 18 over here, because we have different species being involved. Convert grams to mole for the first step. So molars of octane as well. But what number do we need to put in the blank? Do remember, when you look at the number, you look at what relationship this is. Mole and the gram relationship is molar mass. So we know it's 1 mole of anything is formula mass grams. And you calculate the molar mass, it's 8 carbon and 18 hydrogen. You look up the atomic mass and total them up, you'll find out it's 114.3. Okay, so why do we use 1 over here? Oh, because this relationship is molar mass, and molar mass is always defined as 1 mole is formula mass grams. So that's why you have the number 1 in the indicated place. Okay, right. Now, second step. After first step, you have molars of octane. You need to convert it further to moles of CO2. So how do you convert to moles of CO2? So what's retained is this unit. You got to convert it to moles of CO2. So this unit should be cancelled out. That means mole of octane should be written for the next conversion factor. Then you need to convert it to moles of CO2. Okay? So then the same question, I always want you to be 100% clear. What numbers should I write in the blanks for this conversion factor? Do I write a 1 over here? Do I write a 1 over here? No, that's wrong. Okay, basically, you need to look at the relationship as I've been emphasizing all the time. This relationship is molar relationship. So when you look at the molar relationship, you really need to know how to get this molar relationship. You get it from the balanced chemical reaction. Look at the top. So it's 2 moles of octane. 2 is related to 16 moles of CO2. So that's how we get the number. It's 2 moles of octane gives you 16 moles of CO2. All right. Now step 3, you need to convert moles of CO2 to grams of CO2. So you need to cancel out moles of CO2. That's why moles of CO2 is at the bottom. Grams of CO2 is at the top. Right. Then again, the same question. How do I know what numbers I should put in those blanks? Do I put down 2 moles or 16 moles of CO2? But if you put down 16, that means you do not really understand the relationship. How do you get the numbers for those blanks? You determine the numbers by the type of relationship. Over here, the type of relationship is over here is mole and the grams. Mole and the grams means that's molar mass. Molar mass is always 1 mole of anything is a formula mass grams. So rather than putting down 16, we actually put down 1 because it's a molar mass. 1 mole is formula mass grams. How do you calculate formula mass? You add all atoms together. It's 1 carbon and 2 oxygen. You put it together, it is 44.01. So 44.01. Okay, that's why you have all these conversion factors lined up in the way it shows over here. But I just showed you in slow motion how this works. So to summarize this thing, the most important thing is first, you should be able to write down the core relationship, which is the molar relationship. Then, according to what information is given, for example, in this case, it's grams is given on the left side, okay, for octane. So that's why on the left side, you got to extend it to grams. And then you decide, do I stop it here or do I further extend it? Because it's asking you the mass of carbon dioxide. So you need to further extend it to the right side for one more step. And that's the whole analysis. Based on the solution map, then you can write out the solution pretty straightforwardly. One trick is though, if you look at its molar and the grams relationship, that means it's molar mass. So it's always 1 molar formula mass grams. If it's molar and the molar, that relationship is derived from reading the balanced chemical reaction. So the reason you have 16 is because, look at, you have 16 over here. The reason you have 2 over here is because you have a 2 over here. All right. Now for the last relationship, why do we have a 1 here, not 16? Is because grams in the mole is molar mass by definition. So it's always 1 mole of something equals formula mass grams. All right. Okay, that's it for the summary. Now hopefully you will do more exercises on your own. Let's look at a practice. How can the following equations be best interpreted? So when you look at this formula, we can read this as 4 molars versus 3 molars versus 2 molars. Okay? So when you look at that, it's 1 molar. If it says 1 molar of aluminum will react with 3 molars of oxygen. No, that's 4 molars, so this is wrong. It should be 4 molars. Now you look at 1 molars of aluminum produces 1 mole of aluminum oxide. No, it's actually 4 versus 2, or 1 versus 0.1, right? So the next one tells you it's 1 produces 0.5. That's 2-to-1 ratio or 4-to-2 ratio. So C is the correct answer. Okay? 1 molar of aluminum reacts with 2 molars of oxygen. No, it's actually 4 molars aluminum will be related to 3 molars of oxygen. Or 1 mole of aluminum would have 3/3 of oxygen required. Okay? Alright, so basically C is the correct answer. That's the molar and the molar relationship. You basically can do this calculation so you don't have to look up each and every one. For example, I ask you, for 1 molar of aluminum, can you find out how many molars of oxygen this can be? So it's molar relationship, so we write the molar aluminum related to molar of oxygen. So read that, folks. Look at here. I want you to look at here. It's 4 molars aluminum related to 3 molars of oxygen. So we got to be able to do that. So what do we start with? We start with 1 molar of aluminum. That's what's given. Now multiply the relationship, okay, molar of aluminum related to molar of oxygen. What number do we put over there? Read it from the equation. So it's 4 molars of aluminum, because it's molar relationship. You read it from the equation. If it's molar mass, it's always 1 mole versus a certain number of grams. Okay, right? 3 moles of oxygen. So you look here, 3 moles. So this gives you a fourth or 0.75 molar of oxygen. Similarly, you can find out 1 mole of aluminum, how many moles of aluminum oxide can be produced. Okay, all right. But this is just a little bit detailed explanation of how you can get those numbers. Let's look at another example. In this example, we are asked how many moles of oxygen are needed to produce 6 moles of iron 3 oxide, which is Fe2O3. Okay, so when we look at question, what is given? We're given a certain number of moles. We want to find out how many moles. But no matter what you have in the chemical reaction, please remember, first thing you should do is to write out the molar relationship. You start with the one that is given. So information about iron 3 oxide is given, so we're going to write out molar of iron oxide first. Okay, and it should be converted to something related to oxygen or O2. So that's the relationship that you should always write out first. Okay, now we read the details. Okay, do we need to convert this to grams? If so, you extend it to the left side or the right side, or both, or neither. Okay, but how do we know? Because we have 6 moles of iron oxide, so that's where we start. You start with moles, and if we are asked to convert to moles as well, that's where you stop, right? So only this correlationship is needed. All right, so for this reason, we're going to start. You have a 6 moles of iron 3 oxide. Okay, now we're going to convert to moles of O2. So you need to cancel out moles of Fe2O3 and then convert it to moles of oxygen. To remember, moles of Fe2O3 is cancelled. What number should you put down in the mole relationship? You get these numbers from the balanced chemical reaction. So 3 oxygen over here, that's why it's 3. Now iron oxide, it's 2 of them. Okay, so it's 2. So this gives you 9 moles of oxygen. Okay, D is the correct answer. Look at another example. How many grams of oxygen are required to completely burn 5.9 grams of propane? Okay, so how do you do this thing? Do you remember it's asking something related to propane, and you want to find out information related to oxygen. So you start with the molar relationship. It's molar propane. Okay, we want to convert to something related to oxygen. So always write out the molar relationship to begin with. That's the core relationship. Do we need to extend it to the left or to the right? So you are given grams of propane. So to the left side, because it's grams, so you will have to extend it to grams. Right. To the right side, do you need to extend it? Yes, we do, because it's asking you how many grams, not how many moles of oxygen. If it's how many moles of oxygen are generated, then you don't need to extend it to the right side. But it's grams, so we need to extend it. Okay, so basically you have 1, 2, 3 different steps. Okay, how many grams do you have to begin with? It's 5.90 grams of C3H8. So the first step, you need to convert grams to molar. Okay, so you use molar mass. I always want you to write the units first, grams and mole relationship, because you need to cancel out grams. That's why grams over here is the denominator. It's moles of C3H8, which is propane. molar mass is always 1 mole equals to formula mass grams. Formula mass, you calculate C3H8, it's actually 3 carbons plus 8 hydrogens. If you put it together, this will give you 44.10 grams per mole. Or in other words, you can write it as 1 mole of C3H8 is 44.10 grams. 44.10 grams. Okay. Next step, step 2. This is step 1, by the way. Okay, that's our step 1. Right. Now step 2. For your step 2, you need to convert mole to mole. That's this mole to the other mole. So you need to cancel out the moles of one thing, which is propane. Okay, that's canceled out. You need to convert that to mole of O2. Then what number you need to put in? Mole relationship comes from the balanced chemical reaction. So you need to balance the chemical reaction first. Notice this reaction is not balanced because it says it's unbalanced. So you got to balance it. So balance carbon first. So you have 1 over there, you have 3 over here. The next thing, you look at hydrogen. You have 8 hydrogen. 1 H2O only have 2, so you put 4 over here. Now you look at oxygen. On the right side, you have 6 plus 4. That's 10 total oxygen. So you need to put a 5 over here. Okay, balance that chemical reaction. So how many oxygen? So this 5 will be 5. Okay. What about propane? Propane, this happens to be 1, not because it's 1 mole, not because it's 1 mole, just like you have in the molar mass relationship. No, it's because you have a number 1 here. That's why. Okay, that's why you have 1 right over here. Okay, now we have one more step. We gotta convert moles of oxygen to grams of oxygen. This is molar mass. Molar mass is always 1 mole. Formula mass grams. Formula mass for oxygen is 2 oxygen together. Each oxygen is 16.00. Look it up in your periodic table. So if you do 2 times of 16, you have 32.00. Then let's do a calculation using your calculator and find out what the answer is. After calculation, we find the number is 21.4 grams. Okay, or B is the correct answer. Right. Let's look at one more example so you can thoroughly understand how to do chemical reaction based calculation or chemical stoichiometry. Right. In this example, you have a reaction that is balanced. This makes things a little easier. So let's look at what information is given. In this chemical reaction, we ask you how many moles of phosphorus. So phosphorus is P, okay? So we're asking you something related to phosphorus, right? Then provided grams of P4O6, that's tetraphosphorus hexoxide. Okay, so key step, the molar relationship, because P4O6 is known, so you always write the known one first. It's moles of this related to moles of phosphorus. That's the key relationship, which is the molar relationship. Always do it that way. Now we're going to decide, do we need to extend to the left side by converting it to grams or not? So look at what is given. For phosphorus, look at here, I want you to look carefully. Hey, for phosphorus, what is given? It's given grams. Not phosphorus, sorry, it's P4O6. It's grams of P4O6 that is given. So for this reason, for this P4O6, you need to further extend it to the left because it's grams of that thing that is given. Okay, so for this reason, to the left side, you will have to extend it to grams. So P4O6. To the right side, do you need to extend it? Then we look at question. It's asking you how many moles of phosphorus. So we already have moles here. Look at that. We already have moles here. So we do not need to further extend to the right side. So that's the reasoning. Now let's solve the problem. So you started with 15.5 grams of P4O6. Okay, you want to convert after step 1. That's the first conversion factor you're going to use. You're going to cancel out the grams of P4O6, and you want to convert it to moles of P4O6. Okay, now what's relationship? It's mole versus grams relationship. That's molar mass. That means you'll have to calculate that it's always 1 mole is the formula mass grams. So what is the molar mass for P4O6? So basically that's 4 phosphorus plus 6 oxygen. Let's calculate that. So you look up the atomic mass for phosphorus and oxygen, and you put it together, and the total is 219.88 grams per mole, or in another word, 1 mole of P4O6 will be 219.88 grams. Okay, so that's why we put 219.88 over here. That's the first step. This is the first step. Okay, the second step, you convert the mole to a mole of a different thing. So that's the mole relationship. We need to cancel out this mole, so that mole of P4O6 is canceled out. Okay, that's why in this relationship, mole of P4O6 is the denominator. You need to convert it to mole of phosphorus. So phosphorus, you have 4 of them. Remember, mole relationship comes from the balance of the chemical reaction. And for P4O6, what number should you put before P4O6? You read the chemical reaction. Now 1 is not written, so it's this one you have over here. Okay, so the meaning is different. When you look at over here, folks, that's a 1. This comes from the balanced chemical reaction. It comes from over here. It comes from here. But the other number 1, this number 1, when you see, it actually comes from the molar mass definition, which is 1 mole is formula mass grams. So although you have 1 here, you also have 1 in a different place, but those 2 ones mean differently. Okay, so let's do the calculation. After the calculation, we have 0.282 mole of phosphorus. So for this reason, E is the correct answer. All right. Okay, let's quickly summarize this for one more time. For chemical reaction-based calculation, also called a chemical stoichiometry, you always start with the mole relationship, then try to decide whether or not to extend it to the left side and or right side by looking at what information is provided in the question. It is very common that you could have several reactants reacting with each other. Then it's very probable that one reactant will run out first. And the one that runs out first is called the limiting reactant, or so-called limiting reagent. The theoretical yield is the amount of product that can be made in the chemical reaction based on the amount of limiting reagent. Sometimes in the chemical reaction, we would say certain amount of one reactant is reacting with enough amount of the other material then the amount that is provided is the limiting reactant. Okay, actual yield is the amount of product actually produced by a chemical reaction. So you might calculate how much of the product can be generated, which is the theoretical yield. But in reality, you might have lost some of the products you collected because it got dissolved in water. It got lost for in the procedure. So the actual yield must always be smaller than predicted theoretical yield. The percent yield is the actual yield divided by the theoretical yield times 100%. Let's look at a few examples related to the limiting reagent or limiting reactant. So look at this particular example. We ask you find the limiting reagent if 1.8 mole of the titanium is reacting with 3.2 mole of chlorine. So you have two reactants, titanium and chlorine over here. Which one is the limiting reagent? So we will do the calculation based on both reactants. Whichever produces small amount of product will be the limiting reagent. So that's how we do the calculation. So we do this as if we have two questions. For example, how many moles of products can be generated based on 1.8 mole of titanium? That's one question. Then we do another question. Okay, if you are given 3.2 moles of chlorine and enough of the other material, okay, how many grams of the product can be generated? How many moles of product can be generated? That's exactly how we work on it. Okay, so basically, as you can see in this question, we only need a correlationship because you are given moles of the reactants. We want to find out how many moles of products that can be generated. So for the top one, you do the one step. For the top one, you do the one step calculation. Okay, so you're given 1.8 moles of titanium. Then when you look at the balanced chemical reaction, you have a 1 mole of titanium. It's over here. So that's where you get that one. 1 is related to 1 mole of titanium tetrachloride. That's what that is. Okay. That's how you get those ones. Okay, all right. So when you do the calculation, you find out it's 1.8 moles of titanium tetrachloride. Okay, then you base this calculation on the number of moles of chlorine. So you're given 3.2 moles of chlorine, and you do know 1 mole of titanium is related to 2 mole of chlorine. Okay, so that's how you can set this up correctly and make sure the mole of chlorine is cancelled out. So you find out it's 1.6 moles of titanium tetrachloride is produced. So because it's a lesser amount, so that means chlorine is the limiting reagent. That's why. And we also know 1.6 mole of TiCl4 is produced. Right. Let's look at a more complicated situation. Right. But we have done this before. Okay. For example, now we do not have moles to begin with. We have grams to begin with. In this example, we give you a chemical reaction which is already balanced. Sodium reacting with chlorine produces 2 moles of sodium chloride. So we ask you for 53.2 moles of sodium and 65.8 grams of Cl. So you have two different reagents of certain amounts. We want you to find the limiting reagent. So basically what you need to do is you want to convert grams of one reactant to the product. You also convert the grams of the other reagent, okay, to the number of grams of product. Okay, so basically we do this stepwise. So basically it's two separate questions. You work on two separate questions and find out the yield, okay, of the products. So the core relationship, for example, for the top one, the core relationship would be sodium. That's the top one, okay? Molar of sodium, because you have sodium, we want to find out the NaCl, right? Converted to molar of NaCl. Again, that's the core relationship, okay? Since you are given, look at here, everybody, look at the top, you are given grams of Na. So to the left side over here, you should extend it to grams. So grams of Na. Since we need to find out how many grams of NaCl, so for this reason, on the right side, you should convert this to grams as well, because we need to find out how many grams of NaCl can be produced. So write up grams of NaCl. Okay, so based on this map, you have the calculation over the top, which we have gone over again and again. Similarly, at the bottom, what's the solution map? The solution map, the core is also molar of CO2 being converted to molar of NaCl. That's the core relationship. Since it's grams of CO2, look here, folks, grams of CO2 is provided. So that's why you need to extend it to the left side, okay? It would be grams of CO2. To the right side, we also need to find out how many grams of NaCl this is. So this particular solution map tells you how to calculate the number of grams of NaCl, which is detailed, as you can see over here. All right, so that's 108 grams of NaCl, which is small amount. That means CO2 is the limiting reagent. Okay, all right. So based on the limiting reagent, you can calculate the theoretical yield. Okay, because it's given that 86.4 grams are produced. So it's telling you this many grams is produced, or in another way, this many grams are actually produced. So that's the actual yield, okay? It's not the theoretical yield. The theoretical yield is calculated based on the analysis we just went over, okay? So percent yield is actual yield, which is 86.4 grams, divided by the chemical yield based on the lesser amount, because that's how much that can be produced. So 84.6 divided by 108, that gives you 80.0%. So we have been able to do the calculation based on that limiting reagent. Okay. Let's look at one more example. So in this example, you have grams of two different reactants. We ask you to determine the limiting reagent and the theoretical yield. After you find out the theoretical yield, you compare the two results, because it's based on two different reactants. Okay, so that's exactly how you work on that. I want you to look at this on your own, because we are going to go over another example in the next slide, so we can start from scratch over there. Okay, all right. Okay, let's look at the other example, and that's going to help you when I work on that starting from scratch. So in this example, it's asking you how many grams of NO, which is one of the products. Okay, you look at the NO, how many grams of NO can be produced when certain grams of ammonia is reacting with another amount of O2. So you have two different amounts of reactants. So you will have to decide which one is the limiting reagent first by doing two separate calculations. Okay, so the first one is based on ammonia. So it's based on ammonia, and you want to find out how many grams of product, NO. So it's ammonia related to NO. Ammonia is given. So the correlationship for the first calculation would be mole of NH3 because it's given. So you started with given amount. Converted to mole of NO. That's the correlationship. Okay. Since you are giving grams of NH3, so to the left side, you'll have to extend it to grams. On the right side, you also need to extend it because it's asking how many grams of NO. So grams of NO. So that's the first solution map. We started with 14.5 grams of NH3 times now grams of NH3 and a mole of NH3. Okay, so that's the first step. So this is molar mass relationship. 1 mole is formula mass. Formula mass is a 1 nitrogen and 3 hydrogen. You calculate that. Okay, so this gives you let me just calculate that. So this is 1 nitrogen plus 3 hydrogen. Okay, this gives you 17.03 grams per mole. So it's 17.03. Okay. Next step times. So basically this is the first step. Now second step, you need to convert a mole of NH3 into mole of NO. So you find out moles of NH3 is 4 moles of NH3. Because it's molar relationship, you have to look at the balanced chemical reaction. It's 4 moles of NO as well. So it's 4 moles of NO, right? Times, now this is step 2 by the way, okay? Step 3, convert back to grams. So it's mole of NO. Convert back to grams of NO, okay? So its molar mass is 1 mole is 1 nitrogen plus 1 oxygen. Okay, 1 nitrogen is a 14.01. 1 nitrogen is 14.01. Okay, so 14.01 plus 16.00. This gives you a 30.01. Okay, so 30.01. So I'm going to erase the other things. So I'm going to erase this one. Okay. Erase that. Erase that. Erase that. Right. After the calculation, let's see what number we have. This gives us 25.6 grams. So similarly, you can do the other calculation based on chlorine. So I'm not going to go into that much detail this time. Okay, so it's based on oxygen. Sorry, okay. Based on oxygen. So it's going to be converted to mole of oxygen, then mole of NO, then mole. Grams of NO. The correlationship. Okay, so we're going to write this calculation stepwise. So times, again, grams of O2 is cancelled out. We have a mole of O2, that's molar mass. 1 mole is O2, is a 2 oxygen, so it's a 32.00. Okay, look up at the atomic mass for oxygen, then times 2 because it's O2. So now we convert mole of O2 to mole of NO. Mole of O2, it's 5. Mole of NO, it's 4. Mole of NO is 4. Now convert mole of NO back to grams of NO. So, alright. It's molar mass, so 30.01. We do this calculation, right? The number is 9.15. 9.15 grams. So since 9.15 is the smaller amount, so that is the amount that can be produced. Okay. By the way, oxygen will be called the limiting reagent or limiting reactant. Limiting reagent. All right. Okay, that's almost all we need to talk about. We have one more topic, which is more conceptual. We're going to go over that. So that is enthalpy. So what is enthalpy? Enthalpy is simply a measure of how much heat is being released or absorbed in a chemical reaction. For the chemical reaction that releases heat, we call that exothermic. Okay. The reaction that absorbs heat, we call that type of reaction endothermic. And the amount of thermal energy that is emitted or absorbed by a chemical reaction under conditions of a constant pressure, we call that enthalpy. Right. So the heat, let's use Q for the heat. Q at the constant pressure is the same as enthalpy. Okay. By the way, Q under constant pressure can be written as Q with a subscript P. Okay. Enthalpy is written as delta H. Okay. If you want to specify it's for the reaction, you can use a reaction as the subscript. QP is delta H for the reaction. Basically, enthalpy is the measurement of the heat under constant pressure. If it's exothermic, that means it's releasing heat. Endothermic, that means it's absorbing heat. About the sign of these different quantities, okay, if the energy is flowing out of the system, then we use the negative sign. For example, if you have delta H for the reaction equals negative 25 kilojoule per mole. Hey, that's a negative number. Negative number, that means the reaction is exothermic. Okay. Another example. So if you have a delta H that has a positive number, let's say positive 38 kilojoule per mole. So this just tells you the reaction is endothermic. All right. When you have an endothermic reaction, you start with lower energy. That's where you start. That's the energy. Okay. Endothermic, you gain energy by absorbing heat. So the products will have higher energy in the end. So this represents endothermic reaction. For the exothermic reaction, that's opposite. You start with higher energy, okay, then you release heat. So the total energy in the end will be lower. That's the exothermic process in the chemical reaction. Okay. All right. Look at a couple of exercise. One exercise over here is the process of water condensing. Is it endothermic or exothermic? So how do you condense water? The opposite for condensation is the vaporization. When you vaporize water, it absorbs energy. When you condense water, the opposite is true, which means it's releasing energy. So releasing energy means it's exothermic. Delta H will be negative. So B is the correct answer. Right. So summarize this. Condensation is exothermic. Since we already learned the different kind of phase changes, let's put it together. For example, hey, what about vaporization? Vaporization is How do you vaporize one liquid to vapor, or you add heat to it? So that would be endothermic. What about freezing? How do you change liquid water to ice? You freeze it by lowering the temperature, or in other words, freezing in the process. It will release heat, so freezing would be exothermic. Melting, excuse me, melting would be endothermic because it takes heat for something to melt. Sublimation, endothermic. Deposition, exothermic. Okay. Before we conclude the chapter, I would like to talk about one equipment that we can use to heat up the chemical reaction. That is Bunsen burner. We use Bunsen burner in chemical lab to heat up the reaction. When you look at the Bunsen burner, if there is not enough air, okay, the flame color is yellowish. Okay, when you have more and more air, but not a good enough amount, you actually see more blue color and less yellow. However, when it's optimum amount of air with the fuel or fuel gas, you will see two cones, outer cone and the inner cone. The hottest area is the tip of the inner cone. That's the hottest area. All right. When you have too much air, you will see flaring of this whole flame. So that's not ideal either. So, all right, that's it. Have a good day. See you next time.